Hello all. I hope that this video does not come very late for the Unit 6 test. I have a feeling that you guys are gonna take it probably this week, and I have seen many requests for this one in the comments. So let's dive in. This is the Unit 6 past paper from October 2025, so it's the most recent one, okay? So let's dive in. So question 1. A student investigated the oscillation of a trolley between two springs using the apparatus shown. All right. Okay. The student displaced the trolley towards a stand until one spring was compressed. So I guess they mean towards a stand. So this way. Okay. So the spring was compressed. She released the trolley so that it oscillated horizontally. So I mean, if you push it here, I guess, and release it, you're gonna have an oscillation like this, back and forth between the two stands, this one and this one. Okay, the student measured, okay, the student used, a stopwatch to measure the time for multiple oscillations. She repeated the measurement and calculated a mean. Describe two techniques the student should use when timing these oscillations. So, okay, she can use a marker, a timing marker, okay? She can use a timing marker at the center of the oscillation. At the center of the oscillation. Okay, that's one thing, and this is done because the center gives a maximum speed and cleaner timing. Okay, that's the one technique she can use, and I will need a clean page. I wrote too much, I'm sorry. And the second technique is to start timing after several oscillations. Okay, and the reason for this is to reduce the percentage uncertainty. All right, let's move to part 2 of question 1a. Explain how using a video camera could improve the results. So okay, so with a video camera, I promise to write a more readable letters, so I will try again. So with a video, we can slow what am I trying to say? I'm trying to say that we can see the video in slow motion. So okay, maybe let's write it this way. So we can see the video in slow motion. Hence, it's easier to judge when one oscillation is completed. Okay, so this is my response. I want to check the mark scheme. I haven't actually. So Sometimes I just answer these questions on my own. So, okay, they say that the video camera can record in slow motion, okay. So judging when a whole oscillation is complete is more accurate. Okay, so it's the same as my answer. So let's move on. Okay. Let's oh, there's a part B. Okay, we continue then on the same problem with oscillation. Okay. The student recorded the following measurements. Calculate the mean period of the oscillations. So, okay, how many measurements do we have? Wait, now I'm confused. What do they mean? They mean the period for one oscillation. Okay, so first we have to average the time for 5 oscillations. So 5t, let's call it average, would be 5.25 plus 5.16 plus 5.21 plus 5.19 over 4, right? Because we have 4 measurements. Okay, let me quickly calculate this. Today I'm doing things a little bit on the fly, so that's why I'm a little bit slower. Okay, so this is 5.2, yeah, let's call it 5.20 actually, okay, seconds. And the reason why I use 20 is because we have 2 digits after the dot, so yeah. Okay, and we have to divide this. So to find the period, we have to divide 5t average by 5, right? So 5.20 over 5 yields 104, okay? So 104 seconds. And determine the percentage uncertainty in the mean value of t. Okay, first of all, we have to find okay, the absolute uncertainty is gonna be the half range. Okay, so the half range would be the largest value 5.25 minus the minus value, which is 5.16. So 5.25 minus 5.16 over 2 yields 5.25 minus 5.16 over 2. Let's call it 0.05 seconds, which means that the absolute uncertainty in t will be, you have to divide that by 5, right? Because that's the half range, that's the absolute uncertainty in the 5t, okay? So we have to divide that by 5, and we find just 0.01 seconds. And then the percentage uncertainty is 0. Okay, I'm going to use a clean page. So the percentage uncertainty in t will be the absolute uncertainty in t over the value over t times 100, right? So let's write 0.01 over 104 times 100 would be 0.9%. Okay, let me check the mark scheme. It's in front of me. You can't see it, but I can. So, all right, yeah, this is exactly what they found. And by the way, you could let me see. The percentage uncertainty in the period, okay, will be exactly the same as the percentage uncertainty in the 5t, okay, because they are proportional to each other pretty much, okay? So they will be the same, right? Part C. Okay, let me see. The student investigated how T varied with the mass of the trolley. She recorded the following data to draw a graph, okay? These measurements are a little bit all over the place. Okay, criticize the recording of the data. So first of all, there are no units for the mass. So no units for the mass. No repeats. Okay, they start at 1.3, 1.8, 2.3. Okay, that's good. Is there anything else? Very few points. Just 3 points is not enough. Let me see. This measurement here looks a little bit off compared to the other two. I mean, it should be, I mean, t should be in between. So I guess they forgot to divide by 5 there, okay? So at the 1.8 measurement, t is too large. Okay, I'm gonna move to the clean page. Too large compared to the other two values. Okay, I think that's plenty. The question awards 2 marks. So usually this means that you have to provide 2 points, and we have written 4, so that's plenty. All right, moving on to question 2. A student investigated a current carrying coil using the apparatus shown. Okay, there is a small coil over here, a large coil, a connector. All right, so what's the question? The student placed the small coil inside the large coil and switched on the AC power supply. Okay, it's the large coil that is provided with the AC supply, okay? An EMF was induced across the small coil. The induced EMF was displayed on the oscilloscope screen as shown below, okay? The vertical scale was set to 5 millivolts per division. Determine the maximum EMF induced across the small coil. Okay, so we have to count the squares, I guess. So we have 1, 2, 3, 4, 5, 6, 7. Okay. 7 point something pretty much, right? So max, let's see, max EMF would be it's quite 7.2 maybe 7.2, and it's 5 millivolts per division. Let me see, 7.2 times 5 gives 36, but this should be divided over 2, right? Because this is from the minimum to the maximum. Okay, so about, I would say 18 millivolts. Let me check the mark scheme really quick. They say 18.5. Why though? So okay, let's count again. So 1, 2, 3, 4, 5, 6, 7. Oh, okay, I forgot to check this. So yeah, it's 7.4 actually. Okay, now I see it. So this is 2 divisions there, so 7.4. Okay, so if we change this to 7.4, I'm sorry guys, 7.4. Okay, let me erase the whole thing. So 7.4 times 5 over 2 yields 7.5, 7.4, sorry, times 5 over 2 yields 18.5 millivolts. I'm sorry, I didn't see the scale there, okay? So, see, I make mistakes when I don't work out the problem in advance, and I'm working it on the fly. So, part B, the connectors were a distance x apart as shown below. The relationship between the the induced voltage across the small coil and the current I in the large coil is Z n I over x, where n is the number of turns in the large coil and z is a constant. The student varied I to obtain results and plot a graph to determine a value for z. Complete the circuit diagram to show the circuit the student should use. So, let me see again what's going on here. So, you need an ammeter in series with the large coil, I guess, to measure the current, right? So something like this. And what else? You need a resistor, right? So you can vary a variable resistor actually to vary the current. So let's put the variable resistor over here. Okay. So that's a variable resistor and an ammeter. So let's write it down actually. So ammeter and variable resistor. And the moment of truth for me is to check the mark scheme. All right, okay, and they also have a switch. Okay, I guess a switch is useful as well. So something like this. Oops. So a switch. Okay, and they also put the ammeter in series with the large coil. So they put the ammeter here in the mark scheme, but I guess it's fine to put it in the way we did. So okay, we need to measure the current and a way to vary the current, and the variable resistor is perfect for that. So part 2, it seems like a long writing problem. Okay, devise a method the student should use to determine a value for z. Your method should include the use of a suitable graph. All right, so okay. All right, let me think. So okay, you have to measure x. So measure x with a meter ruler. Okay, count the number of turns. Count the number of turns in the coil. Okay, so let me transfer the equation over here. So V is Z n I over X, Z n I over X. So we need X, okay, we need the number of turns, and now we need I. Okay, so you must keep n and x constant and vary I pretty much, right? And vary I. Okay, so you can vary the current I and measure V for at least 5 different values of I, and plot V versus I find the gradient. The gradient is going to be equal to, let me see, z times n over x. Therefore, z, the one that you're looking to find, is going to be x times the gradient over n, okay? And since you measured x and n over here in the first two steps, you will be able to find z, and that's it. That's the answer, okay? It's a 6-mark question, therefore we have to provide about 6 points, did we? So 1, 2, 3, 4, 5, and I guess 6 will be the discussion about the gradient and how it's connected to z. All right, so let's do question number 3. Capacitors. All right. A student investigated the discharge of a 680 microfarads electrolytic capacitor. All right. She connected the capacitor and a resistor with resistance R in a circuit as shown. Okay, the student moved the switch to position 1 to charge the capacitor. Describe 2 safety precautions the student should take when using an electrolytic capacitor. Okay, so fully discharge before use. It's always good with capacitors. So fully discharge the capacitor before use. Okay, what else can we write? Do not exceed the working potential difference. Okay, so do not exceed the working potential difference. Correct polarity always helps. Okay, let me check the mark scheme, make sure. Okay, they mention in the mark scheme, they say any two from do not exceed the working potential difference for the capacitor. Connect the capacitor with the correct polarity. Okay, discharge the capacitor fully before handling. Okay, so perfect. Okay, let's move on. Part B. As the capacitor discharges, the current I is related to the time t by the expression the exponential decay, the familiar one, where I naught is the current when t is 0. Explain how a graph of ln of I against t could be used to determine a value for R. Okay, this is a very easy problem, in my opinion. Okay, I promised myself back when I started teaching physics in the very distant now 2009 that I will never use the words it can be easily shown or this is easy, etc. But okay, I think this is straightforward. Okay, so we take the exponential decay graph and take the ln in both sides. So ln of I is ln of I naught minus t over rc, which has the form y is equal to, let's call this c plus mx, right? So the gradient is equal to minus 1 over rc. Okay, so r is minus 1 over c times the gradient. Okay, and that's the answer. Simple as that. Okay, it's a linear equation, a linear form, so it's very easy to find. All right. Part 2, the student moved the switch to position 2 and immediately started a stopwatch. She recorded I every 10 seconds. The student recorded the following results. Okay, plot a graph of ln of I against t on the grid opposite. Okay, use the additional column to record your process data. You should keep the values of I in milliamps. All right, so let's call this ln of I in milliamps. Okay, let me see. Okay, this is the point where I will do the calculations, but you will see the final results because this is YouTube and I'm gonna cut this part of the video. Okay, so I'm gonna work out the results now. So okay, here are the results, and now again I'm okay. Actually, I'm gonna show you a little bit how I'm gonna do this. Okay, it's time to draw the graph. I want to make use of the whole grid that they give us. So okay, the way I do it is, okay, let's draw a horizontal line here, okay, down there, and then a vertical up here, so we make use of the whole space. All right, so we will have time in seconds over here, and the range is between 10 and 60 seconds. So okay, we can start from 0 and say that this is 10. So every box represents 10 seconds. Okay. Okay. And now the range in the ln of I is, say, from minus 1.4 to minus 3.6. So 3.6 minus 1.4, that's 2.2. So we can use boxes of size 0.2. Okay, I hope this makes sense. So what I'm trying to say is that this should be minus 3.6. Then, I mean, the very first one, okay? Remember, the axes do not have to start from 0, okay? So minus 3.6, minus 3.4, and this is the point where I will accelerate the video for you, okay? Okay, these are our really nice axes, okay? And then now we will enter the points. Okay, first pair is 10 and minus 1.44. So okay, 10 is over here, and then 44 is over there, okay? And I will continue like this. I will accelerate the video again, okay, obviously. But let me show you one more. For 20, we have minus 1.8. This is very straightforward, okay? Okay, and let's do one more, and then I will accelerate the video. Okay, for 30, we go to minus 225, okay? 30, okay. This is 2. Wait, I'm confused now. I think I made a mistake in the first one, okay? Minus 1.4. So minus 1.44 should be over there. Okay, I'm sorry. And now we have minus 2.25, which should be this 2.3. So every little box is 0.1 over 5 is 0.02, okay? So this is minus 2.2, so 225 should be there. These are all the points. Now it's time to draw the line of best fit. It's a very nice straight line, so we shouldn't have a problem. Let's use a different color. Let's use red, okay? And okay, let me try to go through the points. Oops, don't know why this happened. Is there a way to draw a straight line? Maybe use this and try again. Okay, this did it. Okay, it's a nice straight line, goes through most of the points, so that's good. Okay, this is our graph. If you guys have questions about this, let me know in the comments. But let's move on to part 3. Determine the value of R using the graph. Okay, first of all, we will need, so R is minus 1 over C times the gradient, okay? And C is given, so we'll use it later. But let's find the gradient. And usually I take extreme points. It's easier that way. So let's again use this nice tool there. Let's use a different color. Let's do green. Okay. So we can use, when I say extreme, I mean, for example, over here, and then all the way up there. Okay, that's not a straight line. Okay, let's use this. Okay, all right. Okay, so we have to count those squares. So we have 10, 20, 30, 40, 45. Each of those little squares over there is 2. So, okay, so this is 10, 20, 30, 40, 45, let's say 48 seconds. So that's delta t is 48 seconds. And then in the vertical direction, we need all these. So I'm gonna move over there. Delta of ln of I is, okay, from minus 3.4 to what's that? Minus 1.5. It's minus 144 actually. So 3.4. So minus 3.4 minus of minus 1.44 yields, okay, minus 196. Okay, so the gradient is delta ln of I over delta t, which is minus 1.96 over 48, right? Yes, 48, which is minus 0.04. Okay, let's call it 41 maybe. So R would be minus 1 over 680 times 10 to the negative 6, and then times minus 0.041. Okay, and the result will be 36.01 kilo ohms. And the moment of truth is to check the mark scheme, guys. Okay, so I'm doing that right now. So they find 33.8 kilo ohms. So, okay, we are a little bit off, but within the same order of magnitude. So that's okay. I mean, you can make a better graph and try to match the result of the paper. In the paper, they say that you should find R in the range 32.5 to 34.2 kilo ohms. Okay, our result is a little bit higher. That's fine, but I showed you the methodology and such. So let's move on. Explain how using a data logger instead of using an ammeter and stopwatch will improve the investigation. So the data logger reduces the uncertainty by taking fast and simultaneous readings. Okay, and if we do a higher sampling, meaning taking more points, higher sampling improves the best fit line and accuracy. Okay, let's check the mark scheme. They say that the data logger can take simultaneous readings. The readings will be closer to the true value, so less uncertainty, higher sampling rate. Okay, we set that, and less uncertainty in the best fit line. Okay, so let's move on to question 4, which I believe is the final one, because this is what Unit 6 tests look like. So a student investigated the vibration of a metal wire using the apparatus shown. Okay, we have an AC power supply, an electrical connector, wooden blocks, magnets, a wire, and so on. The student switched on the power supply and the metal wire vibrated with a small amplitude. Notice how this question, by the way, I want to make this comment before moving on, is mostly related to unit, I think 2. It's in unit 2 where we study standing waves. So this is AS level physics, okay? So it's what I say over and over again, that you have to be familiar with all the physics you have done in both the AS level and the A level when you take the A-level tests, the international A-level tests. Okay. The students switched on the power supply and the metal wire vibrated with a small amplitude. Moving the bridge, this thing is the bridge, okay? Moving the bridge, okay, let me erase this, changes the amplitude of the vibration. There is a maximum amplitude when the bridge is a distance L from the wooden blocks, okay? Describe an accurate method to determine the value of L. Okay, so, and this is a 4-mark question. So I guess you have to adjust the position of the bridge to determine the maximum amplitude. Okay. Use a meter, use a ruler, I guess, a meter ruler to measure L. Okay. What else can you do? Let me think. Start. Actually, sorry. Maybe write something like adjust the zero of the ruler to match the wooden blocks, and take several measurements of L. I guess the L should be the middle of this bridge, okay? So that's another thing you can say. So, and take several measurements of L and then take the average. Okay, so that's a possible answer, okay. Part B, the student used a micrometer screw gauge to measure the diameter D of the wire. Explain one technique he should use to determine an accurate value for D. So you have to measure D. It's the thing where you have random errors. So you have to measure D at various orientations to avoid, and then take the mean, of course, to avoid the random error. So take repeat measurements at various orientations and take the mean to avoid random error. Okay, and the reason is that if you, let's say that you're looking at the cross section of this wire from above, it might look like this, okay? So if you measure D along this direction, for example, it's going to be different from this direction. Oops, let me move this. Oops, okay, let me move this down here, okay? So D across the horizontal direction will be different than the D in the vertical direction, and it will be different from this diagonal direction I just showed. Okay, so if you take multiple measurements from different orientations and take the average, you minimize the random error, okay? Which the random error here is due to the wire, of course, okay? All right. So question C. The relationship between the distance L and the mass M hanging from the wire is given by that formula. That scary looking formula, I have to say. L squared is M times G over, okay, that's the weight. And then we have pi rho D squared F squared, okay, where rho is the density of the metal and F is the frequency of the power supply, okay. The student used the frequency meter to measure F. Show that the value of rho is about 8,100 kilograms per cubic meter. So, okay, this is a straightforward problem actually. So we have to solve for rho. So rho is going to be M times G over pi L squared D squared F squared, and I'm gonna walk you through the calculation actually, because I haven't done it. As I said, I'm working on this on the fly. So we have 802 grams, so we have to convert to kilograms by multiplying to the minus with 10 to the minus 3. G is 9.81 like always. Pi is 3.14. L squared is 0.343 squared. D squared is 102 millimeters. So we have to do 1.02 times 10 to the negative 3 squared. And then F squared is 50.3 squared. Okay, I ran out of space there. Let me do the calculation. Okay, I found 8,090.8 kilograms per cubic meter, which is about 8,100 kilograms per cubic meter. Okay, that's good. Let's move on to part 2. Okay, part 2. The frequency meter had a resolution of 0.1 hertz. I guess you can interpret that as the uncertainty in the frequency, okay? And the uncertainty in the mass is negligible. Show that the percentage uncertainty in rho is about 6%. Okay, so let's first write down rho, which is M times G over pi L squared D squared F squared, okay? And we need to find the percentage uncertainty in rho, which will be the summation of the percentage uncertainties in the quantities that do have an uncertainty, which are D, F, and L, okay? Because M does not have an uncertainty, or we will have 2 times, because it's L squared, 2 times the percentage uncertainty in L plus 2 times the percentage uncertainty in D plus 2 times the percentage uncertainty in F. And I have a video explaining why this is so, okay? But the short answer is because we are dividing quantities. So when we divide quantities, we add percentage uncertainties. Okay, so let's quickly calculate all this. So 2 times percentage uncertainty in L will be 0.003 over 0.343. And I'm going to drag the 100 outside of all this. So plus 2 times the percentage uncertainty in D would be 0.02 over 102 plus 2 times percentage uncertainty in F, which is 0.1 over 50.3 times 100. And let's cross our fingers that this is 6%. Okay, let's see. So 0.003 over 0.343, okay, times 2 plus 2 times 0.02 over 102 plus 2 times 0.1 over 50.3, okay, times 100 is perfect. Okay, 6.07%, which is about 6%, and this is good. Life is good. Okay, part 3. Okay, part 3. A textbook states that stainless steel has a density of 7,800 kilograms per cubic meter. Deduce whether the wire could be made from stainless steel. Okay, so the value we found. So we found rho is 8,090.8 kilograms per cubic meter plus or minus 6.07%, right? So the upper limit for the density will be this value, 8,090 plus 6%. So it's going to be obviously above 7,800. So let's calculate the lower value. Okay, so let's multiply our value by 6.07%. This will give you 491 kilograms per cubic meter. We can actually use 491.1. So lower possible value is 8090.8 minus 491.1. So 8090.8 minus 491, I'm sorry, 0.1 gives 7,600 kilograms per cubic meter. So 7,800 kilograms per cubic meter is within our calculated range. Hence, the wire could be stainless steel. Okay, and this is the solution of the Unit 6 paper from October 2025. I hope this is useful. If you find these videos useful, I would greatly appreciate to see some support in the form of my PayPal link. I mean, anything you can contribute would be great so I can continue making these videos. Please share them with people who will find them useful. Let me know what you think in the comments, whether these are useful or not. And please like and subscribe and help me grow this channel, both financially and in terms of subscribers and views and so on. Okay, this is it. I'm gonna see you in the next video. The plan is to continue uploading past papers, but I also like giving lessons, so you might see some lessons coming out. And also eventually I want to break into other fields that interest me. because as you know, I used to be a researcher, so I want to keep exploring concepts and see how this goes. So thanks guys for those of you who watch and like these videos, and thanks for the comments and everything. So see you.